Okay, very good morning to all of you. I'm sharing the QR code. Give the attendance and we will start. Only five students are present and all are sleeping today. Good. Okay, so I think you all have given your attendance, then we can start. Stopping the sharing here and I'll share now. Wait. Okay. Today we will discuss about Anderson Bridge. Okay. So today our topic is Anderson Bridge. So this is Anderson Bridge. Okay. Now this is the diagram for Anderson Bridge because yesterday we have discussed about Hayes Bridge. Okay. So today we will discuss Anderson, then D Sorty, then V. Okay. One by one. So Anderson is also about self-inductance. That is why I have taken Anderson first. So Anderson Bridge, previously we have done Maxwell inductance, capacitance, as well as Hayes. Okay, so all are related to self-inductance. Here also Anderson Bridge, it gives accurate measurement of self-inductance of the circuit. Okay, so this Anderson is also about self-inductance. So Anderson is also about self-inductance. And this is important because in your laboratory, if you are doing Anderson Bridge, then you would be able to understand that how, the calculations are being done in case of Anderson Bridge. Okay. How we use the Anderson Bridge. So come and see this diagram in Anderson Bridge. See, this bridge, you can say it is a advanced form of the Maxwell inductance capacitance bridge. Okay, this Anderson. And in Anderson Bridge, the definitely unknown inductance is compared with the standard fixed capacitance. Okay, so definitely just like the previous Hayes and Maxwell bridge, Hayes or Maxwell में हमने क्या किया था? We had an unknown inductance. Okay, and then we compared it with the with some resistance or with some capacitance. So with the requirement, we have changed the diagram. Okay, somewhere we have connected the capacitor in series, somewhere we have connected capacitor in parallel, like that. Similarly, here in Anderson, the unknown inductance is compared with the standard fixed capacitance. Okay, so where is the capacitance? This is the capacitance. See, in this branch, C has been connected. This is the capacitance. Okay, so so in Anderson, unknown inductance is compared with the standard fixed capacitance, which is connected between the two arms of the bridge. That means if this is the arm we have taken, this is arm A, this is arm B, this is arm C, this is arm D. So here the capacitance is connected. Okay, so diagram is a bit different from the Hayes and Maxwell. But this diagram, you can see it is the advanced form of Maxwell inductance capacitance bridge. Okay, so now we can slowly move to the construction part of Anderson. So in construction part of Anderson, what you will find out? You will find out first of all that the bridge has 4 arms. Okay, what are the 4 arms? AB, then comes obviously BC, then comes CD, okay, and then comes obviously AD. So these are the 4 arms, important arms of Anderson. So this is A, B, this is B, C, this is C, D, and this is DA or AD, whatever. Now the arm AB, follow this arm AB. This is the arm A, this is the arm B. So this arm, particular AB arm, it is having an unknown inductance along the resistance. So which is the unknown inductance? This L1. See, this L1 is the unknown inductance which is connected, which is having internal resistance R1 variable. and connected in series with the circuit. Okay, so this is in the arm AB. Check it out in the arm AB. Now you will see, you will find here, there are two non-inductive resistance in the arm BC. This is BC, okay, and this is AD. AD arm, these two are having non-inductive resistance. Only resistance they are having, that is R3 and R2. And here, in case of the static capacitor and variable resistor are connected in series, okay, are connected in series and placed in parallel with the CD arm. So if this is my CD arm, this is CD arm, then I can see that this with the, if this is the R4, the capacitor is being placed here, and here variable resistance R is here. So static capacitor and variable resistor are connected in series and parallel. That means a variable capacitor is connected in series and this variable resistor is connected in parallel with the CD arm. So the voltage source is applied to the terminal A and B. This is A and C, sorry, A and C. So here the voltage will be applied. Detector, you know, detector is connected between B and D terminal. So here the position of C is a bit different. It is connected here, and here is also a variable resistance small r. Okay, so this is the picture. Now we will do the derivation definitely, but before that, let us come to the phasor diagram of this particular Anderson. Now let us see the phasor diagram. Wait. Okay, look into the phasor diagram very carefully. In this phasor diagram, you will see again a right angle triangle has been drawn definitely. Okay. Now here, first of all, definitely you need to know what is the E. E is the resultant. So resultant is this one. Okay. Resultant is this one. This is different. Another thing what you need to know, this is my E1. This is my E1. Okay. This is my I2. This is my I2. This is my I4. Somehow this is my I4. Okay, and this is one. This one is my I1 R1 plus IR1, because if you, when you see the AB arm, in the AB arm current I1 is flowing within the resistance R1 and small r1. Small r1 is my variable resistance. Okay, and here in case of E3 you can write I3R3, because here I3R3 we can again write like this IC divided by omega C. We can write, okay. And this I1 is equal to I3. Here is written I1. And what are left here, you can write E2. This is the I2 current flowing. So what will be the E2? E2 is I2R2. So you have got E3, you have got E2, you have got E1. Left is E4. E4 we can write simply I4R4. Okay. Simply I4 I can write this E4. So this line, this is the right angle triangle line. This is also this right angle triangle line up to here. And this line is also right angle triangle line. And suppose you see here the dotted lines which are drawn in parallel, that we will see. Just have a look. This with parallel to this line, this dotted line has been drawn. Okay, so I'm giving the parallel sign. Okay, and again, you will see here that this from E1 to E, this line has been joined. Okay, so that we can form a confined structure for the resultant E. So for E1, we can write the formula I1 omega L1. This is for E1. Okay, E2 I told you. I2R2, E4 is I4R4, and E3 I told you. And here at the back portion, you see here, this ICR has been taken because of the capacitor. And that is connected across the arm CD. If you remember the previous diagram, this is IC and variable resistance small r. Okay, so this is the IC current, that is the current flowing through capacitors, because in the figure you can see that the capacitance is connected separately or in series with the resistance R4. So here, see, this is have been drawn like this. So this dotted line again have been drawn parallel to this line. Okay, and this line have been connected directly with the E4, because this IC is connected on that particular arm. Okay, E4, where the voltage is, that particular arm is connected. So it is just like that. Okay, and what is the resultant of E if you're asked? Definitely, this E is the resultant value that we need to know. So here some of the steps have been shown that, see here, some of the steps have, see here I told you that we have to take a reference vector. That is the thing, right angle triangle that we are taking. So they are clearly written that how we can draw this particular, how we can draw this particular, wait, let me tell you this particular, wait, let me, just a second. Yes, now you see how we can draw this particular phasor diagram. First, they have taken I1 as a reference vector. Where is I1? This is my I1. See, wait. Yes. So my I1 is somewhere here. Okay. So this is my E1. This is my I1, this straight line. So this straight line is taken as a reference vector I1. Okay. So first of all, we need to draw I1 R1 in the phase I1. So this is the line I1, and if I try to draw I1 R1 plus R1, so I need to draw this line with respect to this E1, because E1 is the voltage across I1. Okay, so here see the second step 2. Step 2, I told you that I1 can be equal to I3 because E3 is in phase with I3. Okay, so from the circuit, you can see that where is the position of I3 and I3 and I1. Okay, step 3, what they have done about E4. This is the portion of step 3 where they have included ICR. That is the capacitor. Then they have drawn I4. Where is the I4? I can see I4 is this line. Okay, I4 is this line which has been drawn, and then obviously after adding KCL, you can write. Now you know I4. Okay, so if you know I4 and you apply KCL, then you can write this formula because this is the I2. This is your I2. This is your I2. Okay, so you can have this kind of formula if you apply KCL. Then you have to draw E2. Where is the E2? My E2 is somewhere here. Means if you extend the I2, then you will get the E2. Okay, and that will be similarly in phase with definitely I2. And then again you have to apply KVL. If you apply KVL with this resultant, then you will find that E1 plus E3 is equal to E. Okay, or you can say E2 plus E4 is equals to E. That means this is completely by applying KVL. So if you apply KVL, this is the process how you can draw this phasor diagram. Okay. Otherwise, you can check out the circuit diagram that you will draw, this circuit diagram particularly, and you can draw it. Okay. So if it is required, in the question, if you're asked that you need to draw the phasor diagram, so you see here one thing with respect to the phasor diagram. Let me explain you once again that in this particular phasor diagram, you can see that, see, first picture you see about the circuit. You can see that current is entering into the bridge and divided into two parts. First of all, I1, I2. Okay, I1 is with the resistance R1 and I2 resistance R2. So I1 is entering into the arm AB. Means if I take you to the circuit also, you can see what I mean to say. Suppose this is my current I. This I is entering into the circuit. It's divided into I1 and I2, right? Then I1 is entering into the arm AB, which I told you, and causes a voltage drop. So यहाँ पे voltage drop होगा. What is the voltage drop happening here? That is I1 R1 plus R plus this one plus R1. Okay, this is the voltage drop happening here, which is in phase with I1. That means there is no angle difference in between them. So as the bridge is in balance condition, then we can say that same current then pass through the arm BC. This is my BC arm, BC, okay, as well as this AC, okay, BC arms BC and AC. Then you see the voltage drop E4. This is the E4 voltage drop. It will be equal to the sum. You will see here a capacitor is connected. So according to that, we can say IC current is flowing through capacitor. That will be IC by omega C, as I told you, for E4. and definitely another is ICR. Okay, IC small r. So the current I4 and voltage E4 here, that means the current I4 that is flowing, this is I4, and the voltage E4, they are also in same phase, okay? And you will see in phasor diagram, they are on the same line. That means they again don't have any phasor, any angle difference. So the sum of the current IC, that means this is the current that is going towards this terminal C, okay? Dekho, IC is also moving toward this terminal C and I4 is also moving this terminal C. So sum of the current IC and I4 would give rise to current I2 in the arm AD. So if you see here that because in the arm AD, this is arm A, this is arm D. If we see this I2 current is flowing here, so I2 is again entering here. So I can write in simple term that I2 can be equal to the summation of I4 plus IC. I can write now because I2 is entering into the arm CD. Okay, and then it is being divided into two current, that is, IC and I4. So summation of the current IC and I4 definitely is the current I2 in the arm A. So when the bridge is in balance condition, the EMF across the arm AB and the point AD and E are equal. Okay, so we have to keep in that our mind. And what is the E point? This is the E point that E I'm telling you, because just now I told you also that same current is passed through the arms BC and EC. This is the BC arm and this is the EC arm. Okay, this is the EC arm. This is the EC arm, this is the BC arm. As the bridge is in balance condition. So when the bridge is at balance condition, the EMF across the arm AB and the point AD, okay, and E are equal. So the phasor sum of the voltage across the arms AC, that is this one, across the arms AC, this is the A, this is the C, and DE. DE means this one, okay, DE will give rise to a voltage drop across the arm AB. So so the phasor sum of this AD, AC and D, that will give rise to a voltage drop across AD. Okay. So V1 is obtained here by adding what? By adding what? How can we obtain V1? V1 is the voltage. So we can obtain it by adding this I1 R1 plus small r1, this one with the voltage drop. What is the voltage drop across AB arm? I told you that will be omega L1 R1. Yes, omega L1 I1. Sorry, this is my voltage drop across the arm AB. Okay, and the phasor sum of E1 and E3 or E2 and E4 will give the supply voltage. Now, what is that? Let us see that. What is the supply voltage we will get? So you see here in this total Anderson circuit, you can see this L1 is the unknown inductance. We don't know about it, having the resistance R1. Okay, and R2, R3, R4, these are all non-inductive resistance. And what is C4 or C here? If you consider it C4 also, so that C4 is the standard capacitor. Okay, so I'm considering it as C4 for my calculation purpose. Now you see here, at balance condition, what can I write? At balance condition, what can I write? I can write, okay, I'm sharing my whiteboard because here I can't write so much of formula. So at balance condition of the Anderson bridge, I can write from the picture as I1 is equal to I3. Okay, I1 is equal to I3 and I2 is equal to IC plus I4, because I told you that I2 current when entering in the other arm, it is giving rise to two types of current, that is IC and I4. So now I can also write I1R3 will be equal to IC multiplied by 1 by J omega C. Okay. And IC, I also know, IC is known to me as I1 omega C R3. Okay. Other balance, this is one balance condition I can write. Another balance condition we can write as, I am putting a line over here, so I can write another balance condition. That will be somehow I1, okay, in bracket small r1 plus capital R1 plus j omega L1, okay, that will be equal to, I'm writing the balance equation, that will be equal to I2R2, I2R2 plus ICR, okay, plus ICR. Then I can substitute because I know some of the values here. So I can write this as, I can IC in bracket R plus 1 by j omega c, okay, that will be equal to I2 minus IC R4. Okay, so now we can substitute the value of IC that we got from this particular equation. This value of IC I can substitute here. So after substituting, I'm going to the next page. Okay, this is my equation 1. This is my equation 2. I'm moving to the next page. I need to now substitute the value of IC here. So when I substitute, I'm getting I1 in bracket R1 plus capital R1 plus j omega L1, okay, close the bracket, and I need to substitute the value of IC. So it is I2 R2 plus I1 j omega C R3 small r, okay. So now you just solve the equation, and after solving, you will get something I1, here bracket R1 plus R1, okay, plus j omega L1 minus j omega C R3 small r, okay, that will be equal to I2 R2. Okay, this is my thing. And another equation will be I1 in bracket R3 plus j omega R3 R4. This will be plus j omega C R cube R, like this. That will be equal to I2 R4. So these are the two equations I am getting from the phasor diagram and from the E. So now if you try to equate these two equations, we will get something, a big equation, and then we have to separate the real and the imaginary part. Okay, wait for a second. Yes. So now, on equating the equations, we will obtain something. I'm going to the next page because it will take a big space. So it will be I1 in bracket, it will be R1 plus R1, okay, plus j omega L1 minus j omega C R3, okay, small r. You're equating, okay, and I1, I'm writing I1 in bracket, you have to write, wait, I1 in bracket, you have to write R1 R2 by R3 plus, okay, plus j omega C R3 small r R2, like this, divided by R4 plus j omega C R3 R2. So this is my equation after equating the equations, okay? And now you have to separate the imaginary and real part. So I can see from here that my real part is R1, R1 is equal to R1 R3 divided by R4, okay, minus small r1. This is one equation, and the imaginary part is L1, that is equal to, that will be equal to, wait, C R3, you can also write C4, CR3 by R4, and here in bracket you will get, in bracket you will get somehow R4 plus R2, R4 plus R2 plus R2, R4. Okay, and close the bracket. And here some 4 will come. So this is the thing. See, you can follow also this one. Otherwise, let me share my notes with you. Here also, some calculations have been done. Similarly, with the help of this, wait. No, in this no calculation. I have not done any calculation part. So, no, sorry, I have done. So taking the loops and all, just similarly, some calculations have been done here accordingly with the simplifying the parts, that is the real and imaginary part. And here also I've obtained similar kind of formula, that is R1, okay, and L1. So you can take any of this thing I will also share with you. Any of the thing which you like the most, you can take it. So this is also correct. Any one of the thing is correct. Now, after getting this kind of values, and this is the values of L1 and the R1, that means we have separated the real part and the imaginary part. Now comes what are the advantages of Anderson-Reed. One more thing I want to share, that in this particular diagram, which I have not shown you, see here, they have taken the circuit, you know the phasor, okay. Now the portion which we need to find out, they have done the star conversion of that particular thing, okay. So if you do the star conversion, now this particular star conversion they have done only for the portion of E4, okay, of E4. That means you see here R4, this is the capacitor and this is the small r. सिर्फ उस portion का इन्होंने star conversion किया है. Star and delta, ये है star और delta दोनों conversion, and then we have taken each and every arm as Z5, Z7, Z6, जो कि देखो यहाँ पे ये Z5 है, Z6 है, Z7 है. So accordingly, they have just opened the circuit, they have taken the star conversion, and they have, and here what I have done, I have tried to write here, let me clear. Yes, I have to try to write here the equations for this particular R4 capacitor and R. So I have written here the impedance of Z7 and Z6. Okay, Z7, Z6. After that, I have taken the whole circuit. And after taking the whole circuit, now I know what is my value for Z5, Z6, and Z7. So after that, we have just put the values and we have just equated. So this is one process of doing the solving the equations for Anderson in a simplified diagram, which I have done here, and another process which I have just now shown. Now, in this process, if you see, after equating with Z5, Z6, Z7, they have taken the more simplified diagram, this one, where R1 is connected with the unknown inductance R2. If we take the Z7 at this part, Z7 here, and Z5 is right here, and Z6 is right here, and here is the R3. So this is the more simplified diagram we can obtain. So what is the formula we have got finally from here? See, from Z6 we have got this kind of formula, that is R2 R3 in combination with R4. Okay, so here from the previous term they have compared the real and the imaginary part, and same equations you will obtain. So you can, there are two options how you can do the, you can simply do from the phasor diagram, and or you can simplify the full Anderson into a simplified form using star connection, using star conversion, and taking the various impedances, and you can convert it into a simple kind of circuit. Okay, so this process you can also do. So it's a bit complicated as compared to Hayes and Maxwell, this I know, but still you go through the things once, because videos will be uploaded. So dekho, or ye notes I will give you. Okay, once I complete the bridges, I will provide you the notes. Now, two processes are different, but the consequences are same. The results are same. The R1 we are obtaining and the L1 we are getting, that is similar. Okay. Then we have some advantages here that definitely here advantages that you will see here. The capacitor we have added here, it is not variable. Okay. So that is the fixed capacitor, and the balance point is easily obtained in Anderson as compared to Maxwell. And here I told you that they use a fixed capacitor, which actually gives very accurate reading. Okay. And second is here the R1, L1, which we are evaluating, that are independent of the frequency. This is one thing. And inductance we are measuring here, self-inductance, that can be measured much more accurately here in case of Anderson, and accuracy is better than the other bridges. Disadvantages come that circuit has more arms. You can see now in Anderson, definitely the circuit has more components. So it is complex as compared to Maxwell. So if you compare Anderson with Maxwell, you will find in Maxwell only one extra capacitor is added. But here the circuit is a bit complex as compared to the Maxwell. And definitely, as a circuit is complex, the phasor diagram is complex, and so the equation of the bridge is also complex. Okay, so here the expression for R1 and L1 are a bit complicated. Okay, so if anybody tells you to find out self-inductance, then obviously you will prefer Maxwell inductance because it is a bit simpler as compared to Anderson. And here you will see the bridge has an additional junction, or you can see this is not a standard form of AC bridge. AC bridge का जो हमने formula हमें पता है, as you all know, we have applied it in previous bridges. Z1, that Z1, Z4 equal to Z2, Z3, that one formula. That is not applied here in Anderson. So this is not a standard form of AC bridges. So because of the following disadvantages, maximum time Maxwell inductance capacitance is used in the circuit. Okay, so these are very big disadvantages. That is, the circuit is complex, the equation is becoming complex, the phasor is complex. Okay, so if anybody is asked to find the inductance, we straight away go for the Maxwell inductance capacitance bridge because that is much more simpler and easier. Okay, our motto should be always that we use a very simpler model, simpler circuit. Okay, acha. One more thing, Anderson, which I have told you, follow my video once, but still if you face some problem, we will discuss on Monday. Okay, that if it's becoming difficult for you, Anderson, then we will discuss once again Anderson on Monday about this, how they have done the two processes. Okay. So if you have questions, so take it up, follow the video which I will upload, and notes I will give you. That is not an issue. So follow the video that I will give, because in the videos I have totally discussed the equations I have told you, right? So the equation a bit bigger. So if possible, write in your copy. अपने copy में लिख लेना, ठीक है? So actually in case of Anderson, which I have done, I have taken two balance conditions. Then I have compared it, simple. But there in my notes, that process is they have taken the star connection and they have done it. So both the processes are correct. It's not that. It depends upon you which you take up. But this is the thing. Okay. So if anybody have any problem, next class we will discuss. And one more thing, let me share once the QR code with you all, because if anybody has left out, then they can be able to give. Wait. So we will meet on Monday. I mean, tomorrow we will have class from 9:50, the same time. Okay. And thank you for attending to this class. Give the QR code, and after giving the QR code, you will leave. Okay. So thank you so much for attending today's class. I am ending the session here. Okay. Thank you.